Problem number 2. A uniform pool ball of radius r and mass m begins at rest on a pool table. The ball is given a horizontal impulse j of a fixed magnitude at distance beta r above its center, where -1 less or equal to beta less or equal to 1. The coefficient of kinetic friction between the ball and the pool table is mu. You may assume the ball and the table are perfectly rigid. Ignore effects due to deformation. The moment of inertia about the center of mass of a solid sphere of mass m and the radius r is I0 equal 2/5 mr square. In such a problem, solution. In such problem, better to figure what axis of rotation we can choose. Usually we are choosing axis around which we have minimum possible torques. That will be any axis which is perpendicular to vector of j and which is stay in the plane of table. For such axis, let's see, we have all forces which are acting on this ball are force of friction, which are applying in the plane of table. Also we have normal force, and we have a gravity force, which are compensating each other. In any moment, angular momentum of this ball after this kick will be conserved. Let's count initial position. When we hit this ball with impulse j, we can count what is angular momentum for this ball around any axis which belong to this table and perpendicular to this j. That will be j multiplied by r and multiplied by 1 plus beta. That's a distance from this point of j. So that's the formula. After that, this kick, we have ball which is moving and rotating, and we have not connected yet velocity and angular velocity. But later, when ball is stopped to sliding, it has instantaneous rotation around axis of rotation, and we can write this equation: L equal I omega, where I is moment of inertia of this ball around axis of rotation, and the omega is final angular velocity. Due to parallel axis theorem, we can count what is moment of inertia. This is the formula. Moment of inertia equal to moment of inertia around center of mass plus mr square, where r is distance from axis of rotation to center of our ball. That will be 2/5 mr square plus mr square, which is 7/5 mr square. And now we can equalize our results, and we have this equation where omega now equal v/r, because there are no sliding. And finally we got the answer, v equal 5/7 multiplied by 1 plus beta multiplied by j/m. So that's the final velocity. Question B. For what value of beta does the ball immediately begin to roll without slipping, regardless of the value of mu? Now let's count what is initial velocity and what is initial angular velocity. To count what is initial velocity, we just write equation mv0 equal j. This is how we count what is the impulse for this ball. From other hand, we have after this impulse we have rotation around center of mass, and we can write this expression I0 omega 0 equal j multiplied by distance from this axis of rotation, which is beta r. And now we can count what is v0 and what is omega 0. So for body not to slide, we have, and now we can put omega here and find what is beta. Finally, we can find that beta equal 2/5.